Greetings, everyone. This is Traci Marin, and I'm here to introduce you to statistics, a crash course on biostatistics and introduction. I hope you enjoy, and I look forward to hearing your comments and questions as we go through the presentation. First, let's talk about the agenda. What are we going to do in this presentation? We will discuss the basic definition or accepted definition of biostatistics. We will make mention of the importance of statistics in our research. We will discuss briefly some of the commonly used statistical softwares. We will discuss population and sampling as it relates to statistics, different types of stats and data, and the graphs that we can use to represent our data. And at the end, we will have a summary discussion of statistics followed by some information related to normal distribution, which is very important when we begin to talk about what types of tests we're going to choose to analyze our data. So the accepted definition of biostatistics is statistical processes and methods applied to the collection, analysis, and interpretation of biological data, and especially data relating to human biology, health, and medicine. So the tools that we employ are the same when we're talking about business statistics and whatnot, but in particular, biostatistics is there to interpret biological data or assess biological data. So why do we care about statistics? Why is it so important? Well, if you're going to explore an issue that you find important, usually you will start by looking at variables or parameters that seem to have some type of relationship, and this helps you develop a hypothesis. And these hypotheses will drive the development of theories that later can become very instrumental in determining clinical outcome measurements and how we change our therapeutics to help with that. So statistics allows you to actually examine those relationships, make comparisons between different drug treatments or different types of populations, and from those statistics, those analyses, we can determine if there's a difference or if there is something that is better in regards to a particular treatment, for example. And we can take that data and present it with a statistical analysis in a way that people can understand and a way in which we can report the studies that we have explored. And usually when we're presenting that information, we are presenting it with a conclusion that we came up with from the analysis of our data sets. We also like to use statistics to evaluate the credibility of a study. So can we see that there is a significant difference between the groups that we've studied? We can also use statistics to explore other people's study. Can we take their data and employ the same statistics or maybe some different statistics based on how we've analyzed that data and say, yes, we're pretty comfortable in stating that this data set and the study that was conducted is credible. So statistics is very important. You can't ignore it. It's something that is an absolute necessity when you're doing research. Now, a little mention of some commonly used software. SPSS is familiar to most people. It's pretty user-friendly. It is employed mostly by social sciences, but I've also used it in my biological data, with my biological and epidemiological data sets. It does require a license unless you're using the PSPP version. It's compatible with Windows, Linux, and Mac OS. It doesn't require that you know any programming. So if you're a beginner, SPSS is a good venture for you. GraphPad Prism is one of my favorites, primarily because it's easy to create a graph of all different types. And also GraphPad Prism kind of prompts you based on the type of data you have on which statistical test you need to use. That's very helpful. It allows 2D graphing of the basics biostatistics, and it's very, very user-friendly. It also is compatible with Windows and Mac OS. A little bit more complicated are Python and R. And that's only because they require knowledge of their programming language. However, nowadays, there are a lot of open source courses and examples that you can use to practice and learn the programming of Python and R. And I very much encourage you to do that because they're very powerful and they have the ability to use large data sets and employ many different types of statistics and other types of analyses on your data sets. You can use them even for your home financing, which is kind of interesting. R and its libraries implement a wide variety of statistical and graphical techniques, so you can basically find programming language portions online and integrate them into your own programming. And a lot of these languages or packages have already been developed. You just need to know how to implement them. But like I said, there are lots of open source choices for learning and exploring both Python and R. And of course, most of us know Excel. We're pretty comfortable with Excel. It's very easy to use. It does offer statistical analyses and graphing. It's not as user-friendly as SPSS and GraphPad Prism, but it's there for those that are afraid to use the other statistical software packages. And then there are some other commonly used softwares like Minitab, SAS, and JASP. I have used SAS also before. It requires a programming language, but it's not too difficult to learn. If you can do SAS, you can do R. If you can do R, you can do SAS. And nowadays, everything is data-driven, so learning the language of these packages is actually a very marketable skill. Okay, so let's talk a little bit about statistics. There's primarily two different types, descriptive versus inferential. And when we're talking about descriptive statistics, we're basically describing the data set. What does it look like? What's in it? How does it present? It basically provides a simple summary about the sample and its measures. Whereas inferential statistics provide some kind of, let's say, inference about the population. So it's a sample of the population, and from that sample, we assess a particular parameter or variable, and from that assessment, we make an inference about the population as a whole. So this is where real statistics comes into place. We can expand that into categorical or qualitative data versus numerical or quantitative data. Categorical or qualitative data includes characteristics that cannot be numerically measured. So the examples that are provided here are, for example, color, red, blue, green, yellow. You can't really put a number on them. When you're coding, you might, but it's not really a numerical variable. Or the description of an event. Numerical, on the other hand, is a number. So the examples that they gave here are height, weight, length, etc. Anything that would actually be identified via numbers. Now, expanding our categorical variables, we have nominal and ordinal. So in the nominal categorical variable area, there's no natural ordering among categories. For example, gender and eye color. However, ordinal data does have some type of ranking scale. So a common example of that would be the Likert scale, when we're using 0 to 5 or 1 to 5, or a pain scale. On a scale of 1 to 10, how bad is your pain? That is an example of an ordinal scale. And moving on to numerical variables, we have discrete versus continuous. So discrete variables take on a countable number of values. So example, how many tablets did that person take of Motrin? 3 or 4 or 5. The continuous variables can take on any value in some range of values. So this could still be height and blood pressure, but when we're getting down to the decimals and we can have a value that could be 1.1, 1.12, etc., that's where the continuous classification comes in. Now, when we're looking at variables, most of the time, in the simplest version of statistical analyses, we're looking at a dependent variable and an independent variable. The dependent variable is the one that is going to be measured, and we're expecting it to change dependent upon the independent variable. The independent variable, also known as the explanatory or predictor variable, it is an individual variable which has an effect on the dependent variable. So, for example, I might say that my blood pressure is the dependent variable, and my blood pressure is dependent upon the independent variable at the degree of exercising that I'm doing at this moment. So if I'm just walking normally, my blood pressure is normal, it's low. But as I increase my walking intensity, my blood pressure will increase also. So my blood pressure is the dependent variable that is dependent upon exercise, which is the independent variable. So what do we think? Spot quiz. You have different types of painkillers to treat your headache. You want to assess which one suits you best. What is the independent variable? Feel free to enter in your answers. The independent variable is the type of painkiller. So if it's a high quality, strong painkiller, then it is going to treat your headache more effectively. In this scenario, the headache is the dependent variable, and the painkiller is the independent variable. Okay, so let's talk a little bit about populations and sampling. So a population is the collection or set of all the values that a variable may have. But a sample is just a small part of that population. And typically when we're doing statistical analyses, we're doing that analysis on a sample of that population. So this is where inferential statistics comes into play. We use the data from that sample to predict or infer what is happening in that total population. So the sample mean, for example, if we're measuring the mean or calculating the mean, is not the true mean, because the true mean would mean that we are calculating the mean for all of the people in the population. But it's a close mean. So it's not a true mean, but it's a close mean. And remember, the larger the sample size, the closer that mean comes to, the closer that mean gets to the true mean of the population. So there are a few different types of sampling approaches. When we're working in a laboratory, it's a little bit more difficult to do proper sampling. But when you're doing epidemiological statistics and clinical statistics, a little bit easier to do proper sampling because you have larger sample sizes. So number one, we have convenience sampling. In this situation, the researcher may select the most accessible and available subjects in a target population. This is similar to our animal research. This approach may introduce bias and is nearly always non-representative of the target population. Random sampling. In this situation, the researcher may also select the random sample group. This method has been shown to be quite accurate. And the reason is that we're randomly choosing different subjects of the population. So we're most likely to get a good mix of what that population is represented by. Systemic sampling. In this situation, the researcher may select every nth individual, so every fourth or fifth individual, for example, in the study, or may select a more complex approach. I know sometimes they will put numbers in a bag and choose numbers out randomly. There are many different ways to do systematic sampling. Although sampling errors occur in most studies, they can be reduced by using a larger sample size. The more samples you have, the more likely your data represents the population data. Right, so moving on to types of graphs, there are several kinds of graphs or charts, but we're only going to talk about a few of them. Line graphs, pie charts, bar graphs, the scatter plot, one of my favorites, and the histogram. So starting with a line chart, in this situation, we can show the amount of change in the dependent variable, which is represented here on the y-axis, for the different points of the independent variable on the x-axis. So in this situation, the y-axis represents what is changing dependent upon what is happening on the x-axis. We commonly use these when we're doing time points for treatments. Line charts are often used to show trends as well as compare two variables. Pie charts are pretty simple to understand. They're most often used to convey the composition of a population or sample set. So for example here, the red represents probably patients that did not return for a follow-up visit, whereas the blue represents patients that did return for a follow-up visit. The highlight of this graph is that it represents a whole, and each part represents a percentage of that whole. We use these mostly for categorical data, just to understand, what is our data set made up of? Okay, bar graphs and columns. Both bar graphs and column charts are useful for comparing data that are grouped by discrete categories. A bar graph is oriented horizontally and a column is oriented vertically, as you can see at the top and the bottom. And these are, most of you are probably very familiar with this. Bar charts are ideal when you are having several categories to represent. So for example, we have a control set of data. Let's say that is a group of patients that did not receive a drug. And then we gave them drug 1 and drug 2 to see the effect, how effective that drug was at treating whatever particular ailment we were working on. And you can see the same down at the bottom with the column chart. Now, the bottom point here says that column charts are more useful in showing negative values. That is true, but I've seen both of these types of charts represented of positive and negative charts. It just usually depends on your preference for visual interpretation. Okay, and here is an example of a stacked column bar chart. They are useful when you're wanting to show composition of individual categories. So you can see here they have total of 45 and 20 makes up of that cell line 1 and probably 25 makes up of that cell line 2. So this is just a way to demonstrate an additional descriptive presentation of your data. Okay, and scatter plots, my favorite, because they really give you that visual effect of what's going on. They are useful in showing the correlation between two continuous variables. And as you can see on the left side, if the data forms a band extending from the lower left to the upper, meaning it looks like it's going up a hill, then that most likely means that there's a positive correlation between the two variables. That means as one goes up, the other one also goes up, and vice versa. In the middle, you see an example of a negative correlation where it looks like the data is going downhill. In this situation, that negative correlation means that as one goes up, the other one is going down. And when you look to the very far right, it looks like there's no real correlation because you can't visualize a pattern here. So likely there's no correlation. Of course, we do some statistics to see if there is a correlation. Sometimes we can pull one out based on the different types of statistical tests that we use. But scatter plots are very nice for visual effects. Okay, and histograms. Now, when you're looking at this picture is not necessarily a histogram, but it is showing you what the pattern of the bars would represent given different types of distribution. So, for example, on the left side, normal curve, normal distribution would have bars, if this was a histogram, that were small at the outer edges of this mountain and taller in the middle, but they would be equal on each side. If the data presents as positively skewed data, the taller bars would be moved towards the left side of the graph, closer to the y-axis. And then the opposite side, if we had negative skewed data, then the taller bars would be presenting closer to the right side of the graph or further away from the y-axis. So here we have a summary of the different types of graphs. When we want to compare values, we typically will use a column, bar, line, scatter dot, or pie graph. So that means I want to compare what was my blood pressure when I was walking compared to when I was running. If we want to measure composition, for example, how many men versus women were in this data set, then we would use a pie or a stacked bar or a stacked column. If we're analyzing trends, then a line chart or a column chart would also be useful. They allow you to see if data is going up or down relative, or we should say a parameter or variable is going up or down relative to the independent variable. Now, if we wanted to understand distribution, we would use a histogram, a scatter plot, or a bar. And understanding distribution is very important because it helps you choose which types of data, which types of statistical tests you might be able to use on your data set. And if we're looking to understand relationships, we would choose a scatter plot or a line plot. Of course, there are many other types of graphs also. These are just the basics and the most commonly used. So spot quiz, you want to see if there's a correlation between the expression of gene A and gene B. Which plot would you use? A scatter plot, because that shows the nice relationship, if there is one, whether it be positive or negative, between two variables. Okay, and a little information on frequency tables. Categorical variables are often summarized by frequency counts. How many are in each group or category? Relative frequency or percent compared to the whole, or proportion, a number from 0 to 1. There's a cross-tabulation feature in most statistical softwares which allow you to produce the frequency table for categorical variables. And you could easily do this in Excel also. So the example that they gave down here is smoking status in males and females in a clinical study looking at the incidence of lung cancer in young adults. So when we're looking at our male population, we had a total of 10. 6 of them were smokers and 4 of them were not. So we've got a 60-40. This is a frequency table. Females, there were a total of 20. 15 of them were smokers, 5 were non-smokers. So now we have a 70-25% ratio. But when we total them all together, male and females, we have a total of 30 subjects. 21 were smokers, 15 plus 6, that's 70%. And 9, 5 plus 4, were non-smokers, that's 30%. This is an example of descriptive statistics, and it's very useful when we're looking at demographics and trying to make inferences about that. Maybe I shouldn't use the term inference here, but making a prediction. Okay, a little more on frequency tables. Continuous variables can also be summarized in the form of frequency tables. So in this example, we have weight of patients in the cardiology ward of Greenfield Hospital. Total subject number N is 50. So how many of them were less than 50 kilograms? There were 8. That was a total of 16% of the population. How many of them were 50 to 70 kilograms? 10, and so on. So this is also useful in being able to see our data. What does it look like? There are some guidelines that need to be followed when we're using frequency tables. Excuse me. The classes that you're using should be mutually exclusive, meaning they're not overlapping. There should be a very discrete cutoff. The classes should cover the entire range of the data, so 0 to 100, for example, if that was your measurement range. The number of classes and the width of each class should neither be too small or too large. So you want to make sure that your categories are comparable in regards to quantity. And the classes should preferably be of equal width. Now, looking at some ways in which we describe our variables or data sets numerically are the common measures of central tendency. And central tendency basically means how likely does the data move towards the center in a normal distribution pattern. So here we have 3. We have the mean, the median, and the mode, and we will go through these each individually. And then we also have measures of dispersion. That's basically how wide, how spread out is your data set. We use range, interquartile range, variance, standard deviation, and standard error. So first, talking about the mean. Most people are very familiar with the mean. It's arithmetic, and it's calculated based on the sum of all of the measurements divided by the number of measurements, which is N. It is, however, best to use the mean as a measure of central tendency when the data are normally distributed. So the mean represents the population nicely if the data is normally distributed. Median, a little different. Median is the 50th percentile. It's the middle value. So it may not be the mean, but it's the middle. If N, the sample size, is odd, or N, the number of parameters, variables, is odd, the median is then calculated as N plus 1 divided by 2. So for example, if you had a number of measurements equaling 29, the median is 15. 29 plus 1 divided by 2 is 15. If the N is even, the median is the average of the 2 middle observations. So if N is 30, you have 30 measurements, then the median is the average of the 15th and 16th observation. So here we're adding a little bit of mean here, implemented in our median calculation. When the data are skewed, median is the best measure of central tendency. So remember our slide on histograms. We could be skewed to the left or skewed to the right. Positive skew is to the left, negative skew is to the right. And then we have mode. It is the value or range of values that occurs most frequently. So here the data set is 2, 3, 4, 4, 5, 4. As you can see, there are 3 4s, but there are only 1 of each of the other numbers. So the mode would be 4 because there are more 4s than the other numbers. Sometimes there's more than one mode, so we might have bimodal distribution in our data sets. Both modes do not have to be the same height. Modes are commonly used to describe nominal, ordinal, discrete, or continuous data. Well, basically almost all of them. Okay, now we have measures of dispersion. So while measures of central tendency are used to estimate normal values of a data set, measures of dispersion are important for describing its variation around a central value. So when we look at this graph down here, you can see that we have a red curve that looks nicely normally distributed. It's got a central peak and it seems to be equal on the right and left. And then we also have the purple curve, which also seems to be normally distributed, but you can see that the shape of the curve is narrow compared to the other one. So what you're seeing here is that they both have the same mean. Here it would be 3, but the amount of data points that are further away from the mean in the red group is spread out much further. So for example, we have 0 to 3, 3 to 6. That means we have about a 3 standard deviation, plus or minus. Whereas when you look at the purple one, our median is 3, and it looks like our data is spreading out to about 4.5. So our standard deviation here would be 1.5 plus or minus. So it's still important to not only look at what is the mean and what is the shape of the curve, but also understand how far out those data points spread relative to the mean. Now we have standard deviation, often represented there. It gives an indication, just like I was saying, of how the data is dispersed or spread out around the mean. And that's what I was describing in the previous slide. A low standard deviation indicates that the data points tend to be close to the mean, while a high standard deviation indicates that the data points are spread out over a wider range of values. We like our data sets to have a small standard deviation. Variance is basically the square of the standard deviation. So remember, we had standard deviation on the right and the left of the mean. Here they're taking those, either the left or the right, and squaring them to give us our variance. And variance is often used in our statistical calculations when we're looking for t-tests and whatnot. And then we have standard error of the mean, which refers to the change in mean with different experiments conducted each time. And we also like to think that the standard error is probably more representative of the population than the standard deviation of one sample set, because it is using several different sample sets from that population. And then we have range and interquartile range. The range is the difference between the smallest value and the largest value in a data set. Quartiles divide an ordered data set into 4 equal parts, aka quarters, and refer to the values of the point between the quarters. So the lower quartile, Q1, is the point between the lowest 25% of values and the highest 75% of values. It is also called the 25th percentile. It's always a little easier for me to draw this out on a piece of paper to understand percentiles and quartiles. The upper quartile, Q3, is the point between the lowest 75% and the highest 25% of values. It is also called the 75th percentile. The second quartile, Q2, is the middle of the data set, It is also called the 50th percentile, or what we like to also call the median. We mentioned that already. The interquartile range IQR is the difference between the upper Q3 and the lower Q1 quartiles and describes the middle 50% of values when ordered from lowest to highest. The IQR is often seen as a better measure of spread than the range and is not affected by outliers. It's more representative. And here we have the normal distribution discussion, my favorite. When I'm teaching my students, I always remind them that most of the parameters that we use to assess our patients are based on normal distribution. Most of us are normal right in the middle, but some of us are normal off to the left or off to the right. So when the frequency histogram of a set of continuous data is bell-shaped, the bell curve, the data are said to be normally distributed. It is symmetric. It's a symmetric distribution where most of the observations are in the middle, around the central peak, and the probabilities for values farther away from the mean taper off equally on both sides, and that's where the symmetry comes in. So when we're characterizing normal distribution, as you saw previously, the shapes of the curves might be slightly different. Some are taller, skinnier, shorter, fatter, and whatnot, but they all have to have the characteristics of symmetry. The mean, the median, and mode are all equal when there's normal distribution. Half of the population is less than the mean, and half is greater than the mean. And then we're considering the empirical rule, which we'll talk about in the next slide. The empirical rule allows you to determine the proportion of values that fall within certain distances from the mean. This diagram represents that nicely. So here, the empirical rule for the normal distribution gives an idea regarding the proportion of the values that fall within a specific number of standard deviations from the mean. So here, mu represents the mean, and we have -1, +1, -2, +2, etc. Those are different standard deviations from the mean. The rule states that if the data are normally distributed, then 68.27%, 95.45%, and 99.73% of the values lie within 1, 2, and 3 standard deviations of the mean. And this is, again, represented very nicely in this diagram. The empirical rule. So in this session, we covered the importance of statistics. We need statistics. It helps us validate our data. It helps us come up with new hypotheses when our initial hypotheses don't come through. We talked about different softwares that you can use, and most of them are available online. Types of data and variables, different types of charts, frequency tables, a summary of statistics, and what normal distribution is. So in the next session, we will cover types of clinical study design, hypothesis testing, p-values, types of errors, odds ratios, and more. Thank you very much, and I'm going to look at your questions over here on the side. Hello, I just noticed a question about softwares for statistics. I did send the message out, but I have gone back to the slide to reiterate that. SPSS, GraphPad Prism, Python, and R. Also, there was a question about a forest plot. I sent that to all of you. The interesting thing about a forest plot is that it can take on different visual presentations, and it's called a blobogram, which is kind of a strange name, but it's used to graph estimated results from many different types of studies. So it's used for kind of like meta-analysis also. I see a question about, is it possible to find similarity scores between two distributions? If yes, please elaborate. Can you give me a little bit more information on that question? Can you give me an example of what you would be trying to do? I see a question about how to determine enough sample size. What we usually do for that is what is called power analysis. So we take a pilot study, or maybe use a study that somebody else has done, and look at the mean, the standard deviation that we talked about, variance, and the sample size. And there's actually a calculation that we can do for power analysis. And you want to make sure that your sample size is at least going to provide 80% power. So you can actually Google that pretty nicely. Google power analysis calculation, and you'll find that all you need is a pilot study, sample size from the pilot study, mean and standard deviation. I also see a question. Could you please give us an example of how we calculate the quartiles? Yes, I can create an example and send that out for you. Okay, I see a question that says, how about if we have different samples of several repeated group experiments? Can we calculate the mean between the groups? So I need a little bit clarification here. So repeated group experiment, are you doing a repeated measures? Then for each of that measure, yes, you could calculate a mean. But the way you would do analyses on repeated measures requires different statistics. We would have to have a conversation about that. Some of you are asking about whether or not you can receive the slides. The recording will be shared with everyone in about a week, and they will announce that at 9:30.